Hi everyone! This video is all about identifying functional groups contained within organic molecules. So we're going to be making heavy use of table R in this video. So a good idea might be to have table R out with you as you watch this video so you can kind of follow along on your own rather than maybe dealing with any fuzziness this video might have. So first and foremost, we're going to define a functional group just as a group of atoms that have been used to modify an organic compound to give it a unique function or some unique properties. So as you can sort of see in this first molecule that I have drawn out here, it looks a whole lot like butane with 4 carbons, completely saturated. But the big difference that stands out is that instead of this carbon being bonded to a hydrogen, it's actually bonded to an OH. And that's what we call a functional group. We've sort of swapped out a hydrogen for something a little bit more interesting. And as you can see in table R, one of the column headings is functional group. And we're going to be looking for examples of these functional groups in the molecules over here on the right. So looking at that second column, what I notice is that the class of compound called alcohols has a functional group of an OH sticking off of some base compound. So here my underlying compound is this 4-carbon chain, and I've added on this OH functional group that defines something as an alcohol. So if I'm asked to identify a functional group, the functional group itself is this OH right here. And because this molecule has an OH attached to it, we classify it as an alcohol. We can follow the same kind of procedure for these other examples. The second molecule, again, it's got 3 carbons in it, but now what I see that's interesting about it is that at the very end, we've got a carbon double bonded to an oxygen and also have an OH sticking out on the outside. Now, don't be fooled, because we've got this OH coupled with this other modification, we can actually look for this whole group of attachments on table R. And what you're going to find is this matches up exactly with the functional group that's defining an organic acid. So be careful to look, make sure that you're including everything that's interesting about the functional group and matching it exactly with what you see on table R. Notice that this matches better with organic acid than it does for ester because we've got this H on the end that shows up here but does not show up here. So we're going to classify, because of this COOH, we'll classify this molecule as an organic acid because it has the organic acid's functional group. Looking at this third molecule, what I see is a chain of carbon atoms that again has something else interesting on it. We've got in the middle of the molecule this carbon double bonded to an oxygen, and then there's another oxygen on the other side of it. So again, all I'm going to do is look through on table R and try and find what best matches that uniqueness that I see right here. And looking down table R, I see some stuff that's close, but nothing matches perfectly except for ester. The functional group for ester looks exactly like what we see here in this compound. So of course, we'll classify this as an ester. Finally, structure-wise, what I see in this last molecule is some nitrogen, which we haven't seen a whole lot of this year. So I've got a carbon that's double bonded to an oxygen, so that's unique, but it's also bonded to a nitrogen atom. So this whole thing is a unique functional group. And if I look and try and figure out which one best matches what I see in table R, I'm going to land myself down here at the very bottom in a mid, where a carbon and an oxygen are involved, as is a nitrogen. It's the only one that has all 3 of those elements involved in its functional group. And it also says I need an H over to the right of the N. Well, I've got one of those in this compound, so I'll classify it as an amide. The only other thing that could possibly throw you off for this type of functional group classification is if instead of giving full structures, you're given condensed structural formulas. So here we're going to try and pull apart what type of molecule we have based on just plain condensed structural formulas. So here, what I see in the top is that this O really stands out. I've got hydrocarbon, hydrocarbon with this O right here in the middle. And looking at the example column in table R, that condensed structural formula looks a whole lot like this example for an ether, which has a functional group of an O kind of sitting in the middle of the compound. So because that functional group exists, we're going to classify this as an ether. Let's take a look at the second condensed structural formula. As I go from left to right, I see hydrocarbon, 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 and then all of a sudden at the end, this CHO. Now there's nothing that quite matches up in the example column of this formula, so I'm going to have to think about what exactly this might look like. So I've got a carbon, and I know it's bonded to a hydrogen. And since hydrogen can only have one bond attached to it, that oxygen must also be attached to the carbon with its 2 bonds that it likes to form. That gives carbon 3 bonds, and we know that to the left, it's attached to another carbon, which is bonded to 2 hydrogens, and so on and so forth. We could continue to draw this molecule out. What I now see in this molecule is that this is the functional group I'm interested in, and that functional group best matches up with the aldehyde. So I'm going to classify this molecule as an aldehyde. So in a condensed formula, CHO is best going to match up with aldehyde. If we look down a little bit further, we're going to take a look at this third condensed formula. And again, looking from left to right, I see nothing but hydrocarbon until I get right to the middle of this molecule where I see a bromine sticking out. And only one of the classes of compounds that we're interested in contains a halogen, or something from group 17. And that's the halide or halocarbon class. So I know that this is going to be a halide or halocarbon. And when you're actually drawing this molecule out, you know that, like hydrogen, halogens like to only form one bond. So when I try and draw out this molecule, once I get to this C, I know one attachment will be a hydrogen, the other will be this bromine, and then I can continue drawing my molecule. So now I'm following all the bonding rules and still see that this single line attachment to a halogen forms the functional group that I want to see in a halocarbon. Let's take a look at 2 more. In this example, again, moving from left to right, I start out with a hydrocarbon, but then all of a sudden I've got this COC in the middle. And this is a little bit different from the very first example we did, where we ended up classifying something as an ether. Because if I try and draw this out, I've got CH3. I know that's attached to a C. I know that's attached to an O, which is then attached to some CH2 group. So if I try and draw CH2, I know it has to look something like that. And there's my CH3 to end, but I've skipped over this O. I also notice that this carbon is missing 2 bonds to make it a complete 4. And every O needs 2 bonds as well. So if we kind of combine those 2 things together, what I get is something like this, where if I have a carbon that doesn't seem to have a complete 4 attachment scenario, I can draw this molecule out so that every atom can be happy. And when I do, what I end up with is this functional group right here, where I've got hydrocarbon on the left, hydrocarbon on the right, and a double bonded oxygen sitting in the middle. And looking at that, I see that matching up best with the ketone functional group. So I'll classify this as a ketone. Last but not least, I've got another thing that contains nitrogen. So hydrocarbon, 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 nitrogen. If you have a hydrocarbon, no oxygen involved, but there is some nitrogen thrown in there, you know that it's either got to be an amine or an amide. Because there's no oxygen that's categorical of an amide, we know this must be an amine. So hopefully this helps you kind of start to pick apart table R. In the next video, we'll be talking about how to break down the names of all of these different types of compounds and how the rules themselves work for naming different types of organic molecules.